And so this is the first ingredient that will help us figure out how to find these constrained maxes or mins. Because, as was discussed, I believe it was 2 lectures ago, if g is a function that defines this surface in the first place, the gradient of g at x naught already is orthogonal to this tangent plane. So we want the gradient of f at this point, dot product with u equal to 0, where u is a vector in this plane. What we already have is that the gradient of g at any point within the surface, dot product of u is equal to 0. So, actually not, so however many constraints we have this is already satisfied for all of them. So here's what we can do. So if u is a vector contained in all the tangent spaces of g1, g2, up to gm for however many constraints we have. And therefore this gives us that the gradient of g1 dot product of u is equal to 0. Same with g2. And so on down to gm. Okay. So if we have this, and if you can find numbers, call them lambda 1, lambda 2, probably like the Greek letters, such that the gradient of f at this point is equal to lambda 1 gradient of g1 plus lambda 2 gradient of g2, and so on. So if the gradient of f is this linear combination of the gradients of g, because all of these gradients are orthogonal to u, then the gradient of f is also orthogonal to u. All right. So key to finding a constrained maximum or minimum. Okay. What you do is you find a point, x naught, so that the gradient of f at x naught is this linear combination of the gradients of the g's, your constraints. So instead of trying to find a point where the gradient is equal to 0, you want to find where the gradient is equal, it can be expressed in terms of the gradients of g. For some numbers, lambda 1, lambda 2, up to lambda m. You don't really care so much what they are, they just have to exist, you just have to find them. These numbers are called Lagrange multipliers. So that's why finding a constrained max or min in this way is referred to as a method of Lagrange multipliers. Now, all right, so now let's so even though I came up with this by talking about the tangent spaces, you don't really care to know what the tangent spaces are. You just have to find a point, x0, where this happens. Because you know this is true already. This is true for any point. That lies in all these surfaces, defined by these constraints. But you don't have this, necessarily. So, if this can be brought about, if you can find a point where this works, because most of the time it's not going to, you find a point where this works, because this is already true, this will be true as well, and that is what you need for a constrained max or minimum. So f can change, but it can only change in a way that violates the constraints. So that's where it's going to have a non-zero rate of change. So that's why you don't need it to have a non-zero rate of change everywhere. That's why you don't need the gradient to be equal to 0 at this point, x0. Because if it wants to be increasing or decreasing in certain directions, and those directions take you off of these constraint surfaces, let it. You don't care. So, all right, let's step through an example. Let's suppose that your function f of xy is 4x squared plus 9y squared. So you want to find the max and min subject to, we're just going to have one constraint. G is xy is equal to x squared plus y squared minus 2x minus 2y minus 2 is equal to 0. Now, we're just in 2 dimensions now. What kind of shape would an equation like that describe? What?
What do you say?
What?
Is it an oblong circle?
No, it's just a circle.
Just a circle?
Yeah.
Okay.
But minus 2x and minus 2y. By oblong circle, does that mean ellipse?
Yes.
Okay. If the coefficients of x and y were different, then you'd have an ellipse. So the equation of this equal to any constant is an ellipse. But the minus 2x and minus 2y indicate where the center of a circle is. Where's the center? No. Negative 1, 1.
Yeah,
1, 1. Yeah. If it was plus, it would be minus 1, minus 1. It'd be 2, 2. If these were 4, you half it. If you're curious, figure out the radius yourself. Now, so what we need is, when you find a point, x0, y0, so that the gradient of f at this point is equal to just one Lagrange multiplier, lambda, because we only have one constraint, times the gradient of g at x0, y0. So when you only have one constraint, the problem simplifies quite a bit because you just want to find out, is there a point where the is there a point where the two gradients, f and g, are parallel? Okay. All right, so we need the gradients of f and g. Gradient of f. 8x